In order for a limit to exist, the left-hand limit and the right-hand limit must match. A great example of this is when we have a piecewise function. So here in a piecewise function, we have two pieces to this. We have the top function, x squared minus 5, is when x is less than or equal to 3. And the bottom function, x plus 2, we're going to use that when x is greater than 3. So in the example here, we're trying to find the limit of f of x as x approaches 3. So we want just plain old 3. So we need to take the limit as it's approaching 3 from the left and from the right. So the first thing I'm going to do here is I'm going to split it up, and I'm going to say we have the limit as x approaches 3, and I'm going to just start with the left. Okay, it doesn't matter which one you start with, of f of x. So f of x is my piecewise function. I'm going to look up at that function. Where it's 3 from the left, that means that my x's are less than 3 and they're approaching 3, so they're going to be less than 3. Like they're starting below 3 and they're approaching 3. So we're going to deal with this top function. So this is the same thing as just saying the limit as x approaches 3 from the left of x squared minus 5. So now I can use direct substitution. I can plug 3 in, so I'm going to get 4. Okay, so the limit as x approaches 3 from the left is equal to 4. I'm going to do the same thing with the right-hand limit. So I'm going to say that it's the limit as x approaches 3, that's supposed to be a 3 from the right of f of x. So again, we're going to look at our piecewise function. If x is coming from 3 from the right, that means that the values of x are going to be greater than 3. So in this case, we're going to use the bottom function. So I can replace the f of x with the actual function I'm going to use. So I'll say that this is the limit as x approaches 3 from the right of x plus 2, since that's the function that has x values that are greater than 3. Again, we're going to just plug that in using direct substitution. So plug 3 in, 3 plus 2, that's going to give us 5. So now we're comparing the limits from the left and from the right. Since the values are different values, it's approaching 4 from the left and 5 from the right, they don't match. So our overall limit as x approaches 3 of f of x is, going to be does not exist. So remember, they must equal the same thing in order for the limit to exist. It doesn't, so it does not exist. Let's look at another problem. Okay, so here we have 3 pieces to our piecewise function. Okay, that's fine. We have no problem with that. So I want to take the limit of h of x as x approaches 1. So again, I have to use the left-hand limit and the right-hand limit. So for this one, if I look at my functions that I have x is less than or equal to 1. I have x is between 1 and 2 inclusive, and I have x is greater than 2. So if I want it at 1 specifically, I'm going to take the limit from the left limit as x approaches 1 from the left. That's going to be the top function, so of ln x. Now if I plug in 1, okay, the ln of 1 is equal to 0. That's supposed to be 0. Okay, if you remember your logs and exponentials, hopefully you do. So now I'm going to take it from the other side as well. So the limit as x approaches 1 from the right. Now from the right side, I'm going to use this function here, the x plus 6, because it's when it's greater than 1. X plus 6. So I plug in 1, and I get 7. Okay, even though x is greater than 2 here, I don't want to use that function because I want to be coming from the left and to the right of 1. So this function is farther away from 1. It doesn't include it. So we want to make sure that we're using the ones that actually include 1. So again, left-hand limit is 0. Right-hand limit is 7. If I'm looking at them, they're different. So that means the overall limit, it does not exist. So my stylus is not so great. So let's just cross that out and let's just write that it does not exist. And maybe we will write it and maybe we won't. Seems like we might not write it. So let's just, oh no, does not exist. Okay. Yeah, you should write it as this limit equals that, but I'm having some issues. Okay, anyway, and then let's look at the second one. So h of x as x approaches 2. So again, we're going to kind of go on both sides of 2. We're going to go to the left of 2 and to the right of 2. Hopefully we write now. There we go. Okay, so we've got the limit. Pretend that's an m. As x approaches 2 from the left. So from the left of 2, I'm going to use this middle function because it's where it's less than 2. So I'm going to use x plus 6. And I'm going to just plug in my 2. So this is going to equal 8. I'm going to do the same thing coming from the other way. So limit as x approaches 2 from the right. Here I'm going to use this bottom function because that's where x is greater than 2. So that's going to be x cubed. And if I'm just going to plug in my 2 there, 2 cubed is going to equal 8. So I'm comparing the left and the right. They both equal the same value. So the limit, I'm just going to draw a little arrow because my pen's not great. That is equal to 8. Yay! We did it. Okay. And here we're going to look at absolute value functions. So the absolute value can also be thought of as a piecewise function, or you could think of it as being positive and negative. So if we think about an absolute value, right, graph kind of looks like that. We could write this as a piecewise function and say that this is going to be x, because here if we look at like the slope, right, the slope of this side is negative and the slope of this side is positive. So if I look at this side, which is positive, this would be x, and that's if x is greater than 0. And then on the other side, it's a negative slope, so that would be negative x if x is less than, and I'll tack on the equals here. That's supposed to be 0. Okay, so if you want to, when you see absolute value functions, you can change them to piecewise functions if it makes it easier for you. The way I kind of think about it is just what's inside the absolute value has to be positive and negative, right? So if it's positive, absolute value makes it positive. If it's negative, absolute value makes it negative. So regardless of which way you want to think about it, we need to still split it up into the left limit and the right limit. So the limit as x approaches 0, if this wants to work, oops, from the left, let's say. So if I'm coming from the left, that means that what's inside the absolute value has to be 0. Not 0, has to be negative, sorry. So that's going to be negative x. So if I plug in 0 here, that gives me 0. Great. If I take it from the other side, the limit as x approaches 0 from the right, that's going to be the positive. We could see it from our graph, we can see it from our piecewise function, or we can just think about it in terms of absolute value, right? If we take it from the positive side, what's inside is going to be a positive value. So that's positive x. Plug in 0, we get 0. The left and the right hand limit, I'm just, again, for writing purposes, the overall limit as x approaches 0 of the absolute value of x is equal to 0, since they match. Always check to see if they match.